885 degrees Fahrenheit, 475 degrees Celsius, embrittlement. Description of damage. 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement is a loss of ductility and fracture toughness due to a metallurgical change that can occur in stainless steels containing a ferrite phase as the result of exposure in the temperature range 600 degrees Fahrenheit to 1000 degrees Fahrenheit, 315 degrees Celsius to 540 degrees Celsius. The embrittlement can lead to cracking failure. Affected materials. A. 400 series SS, e.g. 405, 409, 410, 410S, 430, and 446. B. Duplex stainless steels such as alloys 2205, 2304, and 2507. C. Austenitic, 300 series, stainless steel weld metals, which normally contain up to about 10% ferrite phase to prevent hot cracking during welding. Critical factors. A. The alloy composition, particularly chromium content, amount of ferrite phase, and operating temperature are critical factors. B. The lower chromium alloys, e.g. 405, 409, 410, and 410S, are less susceptible to embrittlement. The higher chromium ferritic stainless steels, e.g. 430, 16% to 18% Cr, and 446, 23% to 27% Cr, and duplex stainless steels, 22% to 25% Cr, are much more susceptible. Although it has not yet been shown in all 300 series SS weld metals, Sharpie impact testing of Type 308 and Type 347 HS's weld metal aged in approximately the 850 degrees Fahrenheit to 885 degrees Fahrenheit, 455 degrees Celsius to 475 degrees Celsius. Temperature range has found evidence of 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement, with individual sample results. In some cases being less than 15 ft-pound, 20 J, at ambient temperatures. However, 885 degrees Fahrenheit, 475 degrees Celsius. Embrittlement of austenitic stainless steel weld metal historically has not been found to be a significant concern in typical refining applications. C. Increasing amounts of ferrite phase in duplex stainless steels increased susceptibility to damage when operating in the high temperature range of concern. A dramatic increase in the ductile to brittle transition temperature will occur. Duplex stainless steels also need to be cooled rapidly after welding to avoid formation of embrittling phases. D. High temperature exposure is required for embrittlement. A primary consideration is operating time at temperature within the critical temperature range. Damage is cumulative and results from the formation of an embrittling ordered metallic phase, alpha prime phase, that occurs most readily at approximately 885 degrees Fahrenheit, 475 degrees Celsius. Additional time is required to reach maximum embrittlement at temperatures above or below 885 degrees Fahrenheit, 475 degrees Celsius. For example, many thousands of hours may be required to cause embrittlement at 600 degrees Fahrenheit, 315 degrees Celsius. E. As a practical matter, since equipment is typically in service for years, it is often assumed that susceptible materials that have been exposed to temperatures in the 600 degrees Fahrenheit to 1000 degrees Fahrenheit, 370 degrees Celsius to 540 degrees Celsius, range are affected. F. The effect on toughness is not pronounced at the operating temperature but is significant at lower temperatures experienced during plant shutdowns, startups, or upsets. G. Embrittlement can also result from heat treatment if the material is held within or cooled slowly through the embrittlement range. Affected units or equipment. A. 885 degrees Fahrenheit, 475 degrees Celsius. Embrittlement can be found in any unit where susceptible alloys are exposed to the embrittling temperature range. B. Most refining companies limit the use of ferritic stainless steels to non-pressure boundary applications because of this damage mechanism. C. Common examples include fractionator trays and internals in high-temperature vessels used in crude, vacuum, fluid catalytic cracker, FCC, and coker units. Typical failures include cracking when attempting to weld or to straighten bent, upset tower trays made of type 409 and 410 SS. This occurs often with vacuum tower trays of this material. D. Other examples include duplex stainless steel heat exchanger tubes and other components exposed to temperatures above 600 degrees Fahrenheit, 315 degrees Celsius, for extended time periods. Duplex stainless steels are normally limited to a maximum service temperature of 600 degrees Fahrenheit, 315 degrees Celsius. Appearance or morphology of damage. A. 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement is a metallurgical change that is not readily apparent with metallography. B. The existence of 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement can possibly be identified by an increase in hardness in affected areas. Failure during bend testing or impact testing of samples removed from service is the most positive indicator of 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement. Figure 3 January 2001. C. Most cases of embrittlement are found in the form of cracking during turnarounds or during startup or shutdown when the material is at lower temperature where the effects of embrittlement are most detrimental. Embrittled 410 SS has been shown to require a temperature of about 350 degrees Fahrenheit, 175 degrees Celsius, before adequate toughness has been restored. Prevention mitigation. The best way to prevent 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement is to avoid exposing the susceptible material to the embrittling range or to use a non-susceptible material. In some cases, users accept the possibility of embrittlement of non-pressure containing components, e.g. trays and other internals, and deal with the possibility or consequences during maintenance. B. Cracking of embrittled material can often be avoided through temperature controls during startup and shutdown. C. It is possible to minimize the effects of embrittlement through modifications in the chemical composition of the alloy. However, resistant material may not always be readily available in most commercial forms. D. 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement is reversible by heat treatment followed by rapid cooling. The de-embrittling heat treatment temperature is typically 1100 degrees Fahrenheit, 595 degrees Celsius, or higher and may not be practical for many equipment items. If the de-embrittled component is exposed to the same service conditions, it will re-embrittle faster than it did initially. Inspection and monitoring. This damage mechanism is very difficult to find prior to equipment failure. It is also time dependent and may take a while to develop in service. Online inspection is not applicable. Awareness of susceptible equipment can help direct inspection planning. The most effective method of detecting or confirming 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement is removing an impact or bend testing a sample of the suspect material. Failure during a simple bend test is the most common method of confirming 885 degrees Fahrenheit, 475 degrees Celsius, embrittlement in thin components like tower trays. Metallographic examination is typically not effective because the embrittlement causing phase in the microstructure is so difficult to find or see. B. Cracking may be visually apparent in certain types of trays and other non-pressure containing hardware that have cracked during maintenance or repair activities. C. Field hardness testing may distinguish embrittled from non-embrittled material, but hardness testing alone is generally not definitive. Also, The hardness test itself may produce cracking, depending on the degree of embrittlement. D. Hammer testing, field impact testing, is considered a destructive test. Tapping a suspect component with a hammer may crack the component, depending on the degree of embrittlement. Hammer testing might confirm that a component is not badly embrittled, if it does not crack, or that it is embrittled, if it does crack. Related mechanisms. Sigma phase embrittlement, 3.56.